By the end of this module, you will have a basic understanding on clean room system application, how it works traditionally in the Danfoss solution, the key benefits of using a VLT/HVAC drive in clean room systems. Let me start the module with a brief description of the clean room system application. The use of clean room environments in manufacturing, packaging, and research continues to grow as technology advances and the need for cleaner work environments increases. Examples of industries using clean rooms for their products include pharmaceuticals, bioengineering, electronics, aerospace, laser or optic, and advanced materials research. Design of clean rooms includes more than temperature and humidity control. Other factors include control of foreign particle size and count, electrostatic discharge, gaseous contamination, airflow pattern control, and room pressurization. 4 main systems interact in clean room facilities to maintain control of these variables. They are intake fan, air handling unit, exhaust fan, air filtration fan. Supply fan control provides fresh air and controls the pressure in the manufacturing cell. Air handling unit control provides temperature and relative humidity control. Filtration control prevents external generated particles from entering the clean room and maintain the class number. The extract or exhaust fan provides fresh air to the clean room for the workers. Now you have an idea of clean room system application. Now, click on the respective button to view their working in traditional and Danfoss solution, or click on the play button to view the key benefits. We shall now look at a traditional fresh air intake fan of clean room systems. Conventional system have a constant speed fresh air fan. This fan simply pulls the fresh outside air into the system and through a pre-filter to eliminate much of the normal debris and dirt or dust found in the outside air. No modulation of this fan typically exists. In the traditional fresh air intake system, the speed remains constant in spite of an increase or decrease in pressure. As the filter becomes dirty, the pressure drop across it increases. Airflow is reduced and can create pressurization problems in the manufacturing cell. A pressure relief damper is installed typically to maintain the correct pressurization. We find that, in the traditional methods, despite an increase or decrease in pressure, the speed remains constant. So there is a wastage of energy. How can we overcome this wastage? It is where the Danfoss solution comes into play. Let's see how this is done. The fresh air intake fan provides outside air and controls the pressure in the manufacturing cell. A slight overpressure is required in the clean room to prevent infiltration of contaminants, such as particles or gases, from being drawn in from external areas. Instead of pressure relief damper, maintaining the proper room pressurization and a constant fan speed, a VLT/HVAC drive is installed and a pressure sensor in the clean room is used. The pressure sensor is referenced to the area outside the clean room to maintain minimum pressure difference. The speed of the fan will be modulated as the pre-filter becomes clogged and as different exhaust rates are required in the clean room. Thus, in Danfoss solution, any pressure change in the clean room is detected by the pressure sensor, and the VLT/HVAC drive reacts by changing the speed or flow rate of the intake fan to maintain a required positive pressure set point. We shall now look at a traditional air handling unit control of clean room systems. The air handling unit controls the temperature and the relative humidity in the manufacturing cell. Depending upon the design requirements, some air handling units provide 100% fresh outside air, while others use a recirculation method. Constant air volume is usually supplied, and high-efficiency filters are added to provide proper room cleanliness. Two types of efficiency filters may be provided. High-efficiency particulate air filters with an efficiency in excess of 99.97% of free microparticles, or ultra-low penetration air filters with a minimum efficiency of 99.999% for 0.12 microparticles. Thus, in traditional solution, although the fan speed is traditionally fixed, the temperature and the humidity of clean room are controlled by other methods, like for example, regulation of cooling or heating coil valves, humidification, and electric reheat. We find that, in the traditional method, the fan speed is fixed, despite changing room requirements for temperature and relative humidity control. A humidity sensor in the space controls a cooling coil valve to control the flow of chilled water in the cooling coil through a digital controller to condense moisture in the air. A room temperature sensor controls the heating and cooling coil valves to maintain the desired room temperature conditions. If the manufacturing cell needs heating or cooling, a temperature sensor in the room controls the heating and cooling coil valves through a digital controller to maintain desired room conditions. We find that, in the traditional method, the fan speed is fixed, despite changing room requirements for temperature and relative humidity control. So there is a wastage of energy. How can we overcome this wastage? It is where the Danfoss solution comes into play. Let's see how this is done. Recirculation air is warmer than supply air because it has absorbed heat from the loads in the clean room. A VLT HVAC drive is installed to reduce the speed of the fan motor when full airflow is not required for temperature and relative humidity control of the clean room. The existing room temperature sensor can be connected to the Danfoss VLT HVAC drive to control the fan motor speed, while the humidity sensor and a new discharge air temperature sensor control the cooling and heating coils through the digital controller to maintain the desired room conditions. Thus, in Danfoss solution, the speed of the fan can be reduced when full airflow is not required for the temperature and humidity control of the manufacturing cell. We shall now look at a traditional control of exhaust fans in clean room systems. Exhaust fans are used to exhaust air from the clean room. This is done for specific air change requirements or a minimum fresh air requirement. Normal flow modulation techniques are used on this fan, such as inlet guide vane or discharge damper control, as the air is exhausted from the facility and does not have an impact on maintaining the correct class rating of the clean room. Thus, in traditional solution, the speed of the fan remains constant. We find that, in the traditional method, the fan speed is constant, despite the variable air change requirements of the manufacturing cell. So there is a wastage of energy. How can we overcome this wastage? It is where the Danfoss solution comes into play. Let's see how this is done. A VLT HVAC drive can be used to control the exhaust fan speed, depending on the process. Thus, in Danfoss solution, the speed of exhaust fan is varied, depending on the required condition. Use a variable speed VLT HVAC drive simply saves energy, otherwise wasted by other fan modulation techniques, such as discharge dampers or inlet guide vanes, and provides lower maintenance and easily adjusted control. We shall now look at a traditional air filtration fan system for clean rooms. These fans, in combination with the styles of filters, high-efficiency particulate air, or ultra-low penetration air, are the key to meeting the required class of filtration. These high-efficiency particulate air and ultra-low penetration air filters are in the order of 99.999% efficiency filters for the particles of 0.3 microns in diameter. The air filtration fans recirculate air inside the clean manufacturing area at a fixed rate. Air distribution is designed to provide laminar flow regions within the manufacturing area. Fans are sized to provide redundancy in case of failure to meet the laminar flow requirements. The most common design use adjustable pitch vane axial or variable pitch in motion vane axial fans. Since different environment need to be maintained over the life of the manufacturing cell, the ability to provide different airflow rates is important for flexibility when changing products. Now, let's have a look at the adjustable pitch vane axial fan. Depending on the class of filtration required, different velocities are needed. Lower the class rating, higher the airflow through the filters. To accommodate different manufacturing needs, and to provide flexibility, adjustable pitch vane fans can be used. Each time a new environment needs to be maintained, the pitch angle of the fan is manually adjusted. However, this process involves labor and creates a lot of particles in the air when the equipment is adjusted. Typically, these fans require soft starters, mainly to prevent air surge that can push any particles through the filters. Now, let's have a look at the variable pitch in motion vane axial fan. The variable pitch vane axial fan is similar in construction to the fixed pitch vane axial fan. The main difference is that the variable pitch vane axial fan is a constant speed fan with variable pitch fan blades. This is the adjustable pitch vane axial fan, and when a damper actuator is added to it, the fan is adjustable in motion. The advantage of these fans is that they do not require soft starters or labor to adjust their operation. As the requirements change in the manufacturing cell, the vane angle can be controlled by a damper actuator connected to the blade rotation mechanical system. Also during startup, the pitch is slowly opened to prevent any air surge through the filter. These fans require maintenance for proper operation, especially the in-motion adjustable pitch vane axial fan. Use of a VLT HVAC drive eliminates the need for these fans, because the motor speed is adjusted to accommodate the different air flows. Some vane axial fans are also belt-driven by the motor. Starting and stopping the motor may cause the creation of fan belt particles. In an environment where extreme measures are taken to prevent particles from entering the manufacturing area, it is not advisable to use equipment that creates particles. We find that, in the traditional method, the use of the adjustable pitch vane axial or variable pitch in motion vane axial fans for meeting the laminar flow requirement has a disadvantage of labor and maintenance respectively. How can we overcome these problems? It's where the Danfoss solution comes into play. Let's see how this is done. The air filtration fan are the most obvious, and arguably the best VLT HVAC drive application in a clean room facility. By electronically modulating the speed of the fan, the different airflow can be easily accomplished, along with a soft start, with a simple analog input signal. Maintenance requirements are also reduced, but most importantly, additional particles in the airstream are eliminated. Depending on the design, the VLT HVAC drive system can also compensate if another fan breaks down by increasing the speed of the remaining fans. As the manufacturing requirements change, the user simply modified the VLT HVAC drive speed input signal. Thus in Danfoss solution for air filtration fans, as the clean room class requirement changes, the speed of the fans can be varied to meet the new requirements. Let us summarize the main benefits of using a VLT-HVAC drive in clean room systems. In the air intake fan system, a VLT-HVAC drive reacts to change the speed or flow rate of the intake fan to maintain a required positive pressure in the room. In the air handling unit control strategy, the VLT-HVAC drive is installed to reduce the speed of the fan motor when full airflow is not required for temperature and relative humidity control of the clean room. With an exhaust fan system, a VLT-HVAC drive can be used to control the exhaust fan speed depending on the process. In an air filtration fan system, depending on the design, the VLT-HVAC drive system can compensate if another fan breaks down by increasing the speed. Before ending this module, let me give you a brief summary of what we learned. Air intake fan. In the traditional method of air intake fan system control, we saw that in spite of an increase or decrease in pressure, the speed remains constant, so there was a wastage of energy at low flow requirements. But in Danfoss solution, we saw that the VLT-HVAC drive reacts to change the speed flow rate of the intake fan to maintain a required positive pressure set point. Air handling unit. In the traditional method of air handling unit control, we saw that the fan speed is fixed, despite the flow required for temperature and relative humidity control of the clean room, so there was wastage of energy at low flow requirements. In Danfoss solution, we saw that the VLT-HVAC drive reduces the speed of fan when full flow is not required for the temperature and humidity control strategies. Exhaust fan. In the traditional method of exhaust fan control, we saw that the fan speed is constant, despite the variable requirements, so there was a wastage of energy at low flow requirement. But in Danfoss solution, we saw that the VLT-HVAC drive can be used to control the exhaust fan speed, depending on the process. Air filtration fan. In traditional method of air filtration fan system, we saw that the use of adjustable pitch vane axial, or variable pitch in motion vane axial fans, for meeting the laminar flow requirement, has a disadvantage of labor demand and maintenance respectively. But in Danfoss solution, we saw that the VLT-HVAC drive system can compensate if another fan breaks down by increasing the speed